sklearn, linear model, HuberRegressor. Description. The HuberRegressor is a robust linear regression model that combines the best of least squares regression and least absolute deviations regression. It is less sensitive to outliers in the data than least squares regression, while still providing a relatively smooth and continuous error function. Inputs: X the training data, which is a 2D array with each row representing a sample and each column representing a feature. Y the target values for the training data, which is a 1D array. Outputs: Core the coefficients of the linear model, which are a 1D array. Intercept the intercept of the linear model. Steps: The HuberRegressor uses a loss function that is quadratic for small errors and linear for large errors. This means that it penalizes large errors less than least squares regression, making it more robust to outliers. The model fits the data by minimizing the Huber loss function using an iterative algorithm. Metrics: Mean squared error MSE, the average squared difference between the predicted values and the true values. Mean absolute error MA, the average absolute difference between the predicted values and the true values. Visualization plots. Residual plot. This plot shows the difference between the predicted values and the true values. It can be used to identify outliers and assess the model's fit. Scatter plot of predicted values vs true values. This plot can be used to visually assess the model's performance. Fine-tune parameters. Epsilon. This parameter controls the size of the neighborhood around 0 where the loss function is quadratic. A smaller value of epsilon makes the model more robust to outliers. Alpha. This parameter controls the amount of regularization applied to the model. A larger value of alpha penalizes the model for having more complex coefficients. Uncertainty methods. Confidence intervals. These can be calculated using bootstrapping or other resampling methods to estimate the uncertainty in the model's predictions. Challenges and fixes. Challenge 1. The HuberRegressor can be sensitive to the choice of the epsilon parameter. Sample use case that resulted in challenge 1. If epsilon is too small, the model may not be robust enough to outliers. If it is too large, the model may not be able to fit the data well. Fixes to challenge 1. The epsilon parameter can be tuned using cross-validation to find the optimal value. Challenge 2. The HuberRegressor can be computationally expensive to fit, especially for large datasets. Sample use case that resulted in challenge 2. If the dataset is very large, it may take a long time to fit the model. Fixes to challenge 2. The HuberRegressor can be used with stochastic gradient descent (SGD) to speed up the training process.